Welcome to the Odor Always Moves video series, where we will be teaching lessons on odor movement for the canine community. This first video is just an introduction, and we're going to cover a couple of foundational concepts, those being order of magnitude in relationship to odor availability, and the concept of advection. This entire series is dedicated to a dog named Daisy. She was my first bomb dog, and to my knowledge, she was the first Rottweiler in the United States certified and operational as an explosive detection canine. It was watching her and other canines work that made me curious about how odor was moving in different environments and conditions. So that's why this video is dedicated to her. Now, typical disclaimers, the animations and images they're as accurate as I can make them, but in this series they're purposely simplified, and because they're just to show the movement in areas where concentrations develop. They're not meant to quantify actual, odor concentrations for specific materials. And if you want to get to that level, by all means, reach out to me or reach out to other professionals, institutions, agencies, whatever, because there's a lot of resources out there. But this whole series is just to educate people on the basics of fluid mechanics in relation to odor movement. Now, who am I? Well, my name is Troy Keckley, and I've been in the engineering, civil, environmental, and solid waste consulting field for over 30 years. And part of that work does include, analyzing and assessing odor movement in relation to like solid waste industries, that kind of thing. But since 2021, I've also been an operational explosive detection canine handler for the airport police department here in Bozeman, Montana. And that gives me a unique perspective as I have the science and engineering kind of background, but at the same time, I'm the person at the end of the leash. And so that's kind of my approach to this is I want to keep this simple because it doesn't need to be complicated if it, we're not like in a lab, okay? We're out in the field, and complicated just slows things down. We need to keep things simple. So that's who I am. So why am I doing this? Well, it's all about helping translate the complexity of odor movement down to the operational level for both canine handlers and trainers. Because I think the more that we understand the principles behind odor movement, we'll have a better idea of how we should maybe be setting up our searches or approaching different situations. And we're going to be doing this with video images and animations generated by computational fluid dynamics. It's also called CFD, and it's just going to show the odorous gases, movement, and concentration levels in those complex and realistic environments. What these are not dog training videos. Yes, I trained my 2 dogs, but please don't reach out to me for dog training advice. I'm not a professional dog trainer. There are great trainers out there. Reach out to them. So, no dog questions. Now, I approach the whole concept of this like I do my job, in that I look at problems as puzzles. And all the pieces of a puzzle, if you dump it out on a table, but you don't have the box, you don't know what it looks like. Some of the pieces are turned over, you can see the image, others not. And it's not until you start putting those pieces together in clusters that you start getting a feel of what the final picture is going to look like. And data, in terms of problem solving, are pieces of those puzzle. And as more pieces of data are found and put together, the picture of the puzzle becomes apparent and is solved. In the canine world, a successful search is the picture of the completed puzzle. Okay, it doesn't mean you found something. I mean, you can do a search and there can be nothing there, and you search it, everything's fine. Okay, that's a successful search. Or you search it and your target odor's there and you find it. That's a successful search. Now, the reason I bring this up is that odor movement is just one cluster of pieces in that total puzzle. And some people look at this as like, oh my gosh, this is the answer to all my problems. No, it's not. It's just a cluster of data. And it has to be looked at with all the other clusters of data to solve the puzzle. Now, what's important is that in some situations, odor movement will be a massive cluster of data. and it will solve the problem for you. It will make the final picture of that puzzle instantly clear. Okay, and a good example of that is area search. You know, kind of search and rescue, and you got a nice strong wind, and you go A to B perpendicular to the wind source, wind direction, but you're working downwind from the possible location. Dog catches the odor, turns hard into the wind, takes you right to the source. That is what I mean. That's a big cluster. That was what solved it, was that odor moving in the wind. But in other situations, it has a very minimal impact. And so it's in those times that we just ignore it. It's like, okay, this is not a critical factor here. I need to focus on other things. Okay, so that's why it's important that we understand the concept of odor movement, and so not to put too much emphasis on it, when we shouldn't, or ignore it when we should be really paying attention to it. Now, foundational principles. We're going to talk about two of them in this video. The first is order of magnitude. And the main reason I'm doing that is because most of the CFD models that you're going to see in this series show a concentration scale of 2 orders of magnitude. And so it's important that you understand that. But it also will help kind of get a grasp of the vast extent that odor availability exists, and the dogs are able to detect. And the second one is advection, which is just the movement of one fluid or material, liquid or gas, by another fluid. Okay, and then odorous gases, being moved by the air. Well, that's an example of advection. We're going to go into that. So orders of magnitude. Now, don't worry. I'm not throwing any heavy math at you. We're not going to go into scientific notation or log scales or anything like that, and trigger any PTSD from high school math class. Okay, that's not what we're doing here. What we are going to do, though, is understand that it's just factors of 10. For our purposes, that's all I want you to remember. And it's a very effective way of representing large or small numbers, like very, very large or small numbers. And it's the easiest way to kind of remember it is just the shifting of the decimal place one way or the other. So each shift of the decimal place is 1 order of magnitude increase or decrease. So with orders of magnitude, let's use something that we can all envision. So let's imagine that a single tennis ball equals 1 unit of odorous gas. Okay, I think we can all envision a 1 tennis ball. Well, 10 tennis balls are 1 order of magnitude more than the singles tennis ball. Okay, so again, this goes back to just moving the decimal places. I just added a 0 to it. Okay, that's that factor of 10. Well, when we go to the second order of magnitude, it's not 2 times 10. It's going to be 10 times 10, because it's always the factor of 10 from the prior value. And so what that looks like, that means that 2 orders of magnitude is 100 tennis balls more than the original. Okay, so hopefully that helps you envision what we're dealing with here. So how does this apply to canine work? Well, it's important to understand that odorous gases released from a source can vary significantly in quantity, which is all tied to the vapor pressure of the source material and the exposed surface area of that source material. Because that's important to understand. And then the higher that the vapor pressure and or the surface area is, the more gas is going to be released. And conversely, the lower the vapor pressure and or surface area, the less gas is released. Okay, so that's important to understand, particularly when we start talking about odor availability and some of these more difficult to detect sources. So what does this look like in the canine world? Let's go back to what we were talking about with like the odorous gas release and the tennis balls and orders of magnitude. So let's take a look at that. So let's imagine again the odorous gas is the equivalent to 1 tennis ball per second. That's how much is going to be released. And that process from a solid is called sublimation. But let's just, again, 1 tennis ball equals 1 unit of odor, okay, per second. Now, we talked about the 2 orders of magnitude, so let's look at a couple things that, and we're going to be looking at odor sources that are unfamiliar with in the explosives and narcotics world. And I'm not looking at stuff for like human remains detection or, search and rescue type stuff. I don't have information on that. Or even, I also don't have information on the nose work, sports, and scent sports. So we're just going to look at things that I do have data for. And so this gives you an idea of some of the odors that we deal with in the canine world and how much odor is actually coming off of them. And so the low end, our baseline, is going to be potassium chlorate. It has very low vapor pressure, and that's our 1 tennis ball per second, okay? And then the next one up, 1 order of magnitude more, so that's 10 tennis balls. That's potassium nitrate. Again, higher vapor pressure, so more odor is coming off, okay? And this is assuming for all of these that the surface area is the same for all the source materials. And so the 2 orders of magnitude, well, we're getting up to RDX, which is an explosive compound, and smokeless powder, gunpowder, and one of the components of that, which is diphenylamine. Okay, and so those are those first 2 orders of magnitude. That's our 1 to 100 tennis balls. So let's keep going up the scale and kind of see what comes up. So the next one is going to be a group of sources. One is PETN, which is an explosive, and then heroin, which is a narcotic, and more smokeless powder components, which is nitrocellulose. Well, those all come in at 4 orders of magnitude more odor than the potassium chlorate. Okay, and you notice the little pictures off to the far left. Well, the tennis balls you could visually see, okay, that's 1 tennis ball, 10 tennis balls, and a box of tennis balls. Well, the car represents that we're talking a number that 1,000 tennis balls would fill up a small car. And then 10,000 tennis balls with 4 orders of magnitude, that would fill up a big full-size pickup truck. Okay, so I want you to kind of get a scale of what we're talking about in terms of difference of odor availability. So let's go to the next one. This is cocaine and TNT. TNT is just a common explosive, and most people know what cocaine is, just thanks to the movies. So now we're talking, so 5 orders of magnitude. Notice that's 100,000 tennis balls. That's about 3 dump trucks worth. And then, but the cocaine and TNT, well, that's 6 orders of magnitude. That's 1 million tennis balls. Okay, that's essentially filling up a big jetliner. So let's go up to the next one. Ammonium nitrate and black powder. Well, we've all seen those big mine haul trucks where the tires are like 12 feet tall. Well, it would fill up 10 of those. We're talking 10 million tennis balls. That's 7 orders of magnitude more than that start. And then the next is HMTD, nitroglycerin, another explosives grouping there. And that's 8 orders of magnitude, 100 million tennis balls. Basically fills up a large cargo ship. And we're going to go to the next, methamphetamine. Okay, very common narcotics that is kind of the scourge of our society right now, along with fentanyl. And that's 9 orders of magnitude more odor is coming off the same amount of surface area than the potassium chlorate. And that's essentially 1 billion tennis balls worth of odor. That's filling up 3 container ships. And then the last one, so nitromethane and TATP, these are very high vapor pressure sources, and that's 10 orders of magnitude more odor, and it's essentially filling up 3 football stadiums, 10 billion tennis balls. Okay, so it's important that when we look at that and we talk about orders of magnitude, it hopefully gives us an idea of the immense scale of odor availability that our dogs are having to detect and are able to detect. That's the cool part about it, is that they can detect that very low amount while also dealing with the very high amounts. And so something to kind of keep in mind, and that's why we wanted to touch on this, so that we at least have an understanding of that odor availability. So let's take a look at this from the standpoint of, a real world situation. What you see here is a room. It's set up, and you probably recognize this as a canine handler or trainer. We're doing a box drill. We got 14 boxes out there. We got our handler or trainer. A handler is always a trainer in in all honesty. And then the dog's getting ready to do its search, and I'm going to use this to show what 2 orders of magnitude actually looks like. And this is kind of showing that. So the blue color, the one on the left, that's our baseline. That's our 1 tennis ball amount of odor. And then the red up in the middle center of the screen, that's 2 orders of magnitude more odor. Okay, so that's the 100 tennis ball quantity. Now you're looking at that and you're probably going, why? That doesn't look like it's 100 times more odor. Well, part of this is you have to understand that this is showing concentration levels, specifically volume concentration. And what we're dealing with is the odor is not homogeneously spread throughout that shape. It's much more condensed towards the center and very, very dispersed and thinned out towards the edges. Okay, and so that's something to understand. So let's show something that may help you visualize that. Now this is just a top view of that exact same picture, except I did a slice through it. Okay, and it's right above ground level, and the blues is basically the low end, the minimum amount of concentration level, okay, that the scale shows, and whereas the red is the highest level of concentration. Well, you can see that the low amount being released, the 1 tennis ball per second, if you want to go that route, down at the bottom, there's no red other than you can see just a little bit inside the box, and that's where the source is, so I expect that. But then you go up to the 2 orders of magnitude, so yeah, that odor's out there, and it may not look like it's 100 times, further out that you may think, but it's very concentrated near the box and inside the box. And so that's where that amount is being, represented in this image. So hopefully this helps you get an idea of how that odor is spreading out, but that it's not a consistent amount. It varies in density, with it being denser closer to the source, and then getting less dense and less detectable further away. So before we go back, we are going to look at that model, because you notice there was a ceiling fan in it. And we're going to go back to that in a little bit, but I want to talk about advection first, so that we have that foundation. Advection is just the mass movement of something by the motion of a fluid, liquid, or a gas. Okay. The best example of that is smoke being moved by the wind. We've all seen that. That's what it is. Okay. But here's the key. Advection is the primary cause of odor movement. Okay. It's the main driver. Molecular diffusion, pretty slow, pretty minimal. The only time that's really applicable is buried hides. Okay, so advection in our world, that's the main thing we got to be paying attention to. Now, it's important to remember that with advection, we're talking fluids, gases or liquids. Okay, and fluids flow, and in that, they will always take the path of least resistance. And they flow around and over obstacles. Now, speed and turbulence, which we're going to get into in further videos, is they can reduce concentration levels. And so turbulence is the first time I toss that out there, but turbulence is just a result of rapid changes in pressure and velocities of the flow. Okay, and those rapid changes result in reductions in concentration levels. Okay, but again, we're going to get into that in future videos. So let's take a look at this. Now the same situation, but the fan is on. It's turning at very slow speeds, it's like half a mile per hour, and so the airflow is very slow. But you can see the 2 order of magnitude quantity that's being released is moving much further out, faster, and that's not the speed that the gas is actually moving. That's just the visual limits of the concentration levels. So the gas is actually much further spread out, but that's just where it's concentrated enough that we can see it based on our scale. Now this is just going to repeat so we can understand this. So you look at that 2 orders of magnitude one, and it gets pushed out, hits the wall, goes up the wall, starts spreading along the wall, and then it goes across the ceiling. and then it gets caught in the air column of the fan. And as it hits it, it's dispersed. That's what we're talking about, the turbulence. The turbulence of the blades is breaking up. So that's why you're not seeing it. It's kind of slow and trying to establish a consistent concentration level. And then at some point in that column it does, and then it goes down at a higher enough concentration level that we can see. But then our baseline one is very slow to come out of the box. And it does start moving, just like it, because it's the same densities as the other one, but it's just less quantity. And so it moves out much slower, kind of works along the floor, starts to go up the wall, and it would eventually do the exact same shape as the other one if I let the model run long enough. But I think this shows clearly enough. This is the difference between a high odor availability odor in an environment where the air is moving versus a low odor availability source. Okay. So let's take a look at that from a bigger picture. This is actually terrain from Moab, Utah. You can see the terrains, and what I want you to see here is just how it flows with the surface. Okay, you can see the wind is coming out of the northwest initially. It goes down, it hits that canyon, and it flows just like water. And that's what I wanted you to see in this, is it moves just like water. But if you notice something, it's now starting to shift. Well, what's happening is in the model, the wind is changing direction from the northwest up to the north, and it's coming out of the north. And so you can see the upper portion of that scent plume getting oriented with that northerly wind, and it's going to start hitting that canyon. But what may be confusing to you is, why is the other downwind plume still hooking to the east? And then, when it hits that canyon, you'd think it'd flow down just like the last one, but it doesn't. It's hooking off to the east. What's going on? Well, there's a thing in play here, and this is why I wanted to talk about advection and how it flows and how it goes over and around obstacles. Well, what's occurring is this. There's a big rock outcropping that hooks out there, and as the wind shifted from the northwest to the north, it started routing that wind along that outcrop and pushing it to the east. So even though north of that outcropping, the flow is going due south, just in alignment with the wind, but because of the deflection of it, it's pushing the downwind portion of that odor plume way off to the east. So those are things to kind of keep in mind as we deal with advection and terrain and obstacles, and we'll get into that in future videos. So let's summarize this. Well, odor availability is directly tied to the vapor pressure and the available surface area. And it can vary greatly between source material types, as you can see. And we showed it's as much as 10 orders of magnitude difference. And likely even greater when we start adding in oil spill, petroleum products or invasive species or decomposing bodies. I mean, who knows? I don't have data on that, but this just gives you an idea. It's like that's a huge range of odor availability. And then advection is the primary mover of odorous gases. And we're going to get into what is kind of the source of advection, but it can be from a natural or artificial. So we show the ceiling fan and then just the wind in a natural terrain. And then fluids flow around and over obstacles, and the odor will go with it. So it's important that we understand the flow directions and the paths it can take to visualize what the odor is doing in that environment. So, upcoming lessons. The next video that I'm working on is going to cover Bernoulli's principle and the effects of wind speed. We're going to use a search and rescue scenario, a collapsed building search, and then a big building search that shows the effects on how the interior odor movement can be greatly impacted by the exterior wind. And then another video we're working on is the impact of ventilation systems inside structures. For those of us that have to work in that environment, that's a critical thing to understand. And then we're going to get into more search and rescue type scenarios, and just the reason is because they apply to so many of us. And we're going to look at mountainous terrain, and the effects of different wind speeds and terrain, and the orientation of that wind with different terrain types. And then another one based on conversations with several search and rescue people, including dive teams and such, is ways of looking at how odor moves on open water, and then using the triangulation method or center of mass method to locate the source, or at least get you close to it. And then another one is going to be urban terrain. We're going to go into the Venturi effect, and it's in line with Bernoulli's principle, but we'll get into all of that. And then I'm going to work on as many as I can, and hopefully get some ideas from the people in the field like you. So that's it for this first video. I hope you enjoyed it. Hopefully it was beneficial to you and worth your time. If you have any questions, please reach out to me. Here's my email address. And if you are an agency or organization, facility that wants specific modeling or teaching for your group or your personnel, or want to talk with me about doing modeling of your particular facility, please reach out to me. Glad to help you. And if you're just interested in following my dogs and their antics, Instagram is at Rotten Bomb Dogs, so feel free to reach out to us. I thank you for your time. I hope you have a great rest of the day. Thanks.